Hello and welcome to my video. Today we will calculate the sum of the infinite series. So here, a sequence Fn is defined by the following recurrence relation. It says F1 equals 1, F2 equals 1, and Fn plus 2 equals Fn plus 1 plus Fn. Now some of you might have noticed that this sequence is the Fibonacci sequence, one of the most famous sequences. Now let us find the sum of this infinite series, the infinite sum of Fn over Fn plus 1 times Fn plus 2. Before we go, I want to say that, of course, one of the most straightforward way of doing it is just find the general expression and just plug it into this sum, but I am not going to do that. This problem here is actually solvable without using the general formula for Fn. That is, you actually do not have to solve this recurrence relation, which is actually quite lengthy and tricky, including stuffs like characteristic equation and other substitution stuffs. So yes, I am not gonna use the formula for the general term of the Fibonacci sequence. So that might be some kind of the hint, and if you want to try it by yourself, please pause here. And for the rest, let us dive into the solution. Alright, let's start from the recurrence relation right here. From here, we know that Fn equals Fn plus 2 minus Fn plus 1. So this term right here can be expressed as Fn plus 2 minus Fn plus 1 over Fn plus 1 Fn plus 2, which can be divided into two fractions, 1 over Fn plus 1 minus 1 over Fn plus 2. Now this right here is actually very useful expression because it allows us to calculate the partial sum very easily. So let's take a look at the partial sum. Right, so this partial sum is 1 over f k plus 1 minus 1 over f k plus 2. And this right here is actually a telescoping sum. So if we actually write down the sum, it is this. So you can easily see that there are parts where cancel out, and the only remaining terms are 1 over f2 minus 1 over fn plus 2, and since f2 is just 1, we have 1 minus 1 over fn plus 2. Okay, so we have a much more simplified expression as the partial sum, and actually the alternate approach you can take right here is to simply use the general expressions for fn plus 2 to obtain closed formed expressions for the partial sum. But like I said previously, I am not going to use the general expression when solving this problem, so let's just forget about that. So instead, we will make the most out of the given recurrence relation, which is this, and actually try to obtain some kind of inequalities. Okay, but why do we need such inequalities? Well, in order to actually find the sum of the infinite series, we have to take the limit where n goes to infinity. And we know that the Fibonacci sequence Fn is an increasing sequence, at least from n equals 2. And here some of you might say, oh well, if Fn is increasing, then this reciprocal term right here must approach 0 when n goes to infinity, right? But actually, that might not be always the case. Well, what if Fn approaches to some finite value for large n instead of, just growing infinitely? Well, then, in that case, this reciprocal term do not approach 0, right? So we cannot just simply guess and say that this reciprocal term goes to 0. We have to actually logically prove it. And in order to do that, we are going to need some inequalities. Right, so first, let's take a look at F3. By recurrence relation, this is F2 plus F1. And since F2 is equal to F1, we have F1 plus F1, which is 2F1. And we also have, since F3 is F2 plus F1 and F1 is positive, we can say F3 is greater than F2. Okay, next, take a look at F4, which is F3 plus F2. But here, F3 is clearly larger than F2, so we have F2 plus F2 with inequality sign. So F4 is greater than 2 times F2. And if we do the similar process here, F4 equals F3 plus F2, so it is clearly greater than F3. And for the F5, the process is essentially the same. So let me just quickly write it. This is larger than F3 plus F3, which is 2F3. And F5 is greater than F4. And we can go on and on. So what we finally have here is, from this part, we obtain Fn plus 2 is greater than 2 times Fn, and from this part, we obtain Fn plus 2 is greater than Fn plus 1. And let us actually rewrite these former parts right here. So first we have F3 equals 2F1 and F4 is greater than 2F2 and F5 is greater than 2F3. It goes on and we have Fn plus 1 greater than 2Fn minus 1 and Fn plus 2 is greater than 2Fn. Right? What we're going to do next is multiply all of these terms, and since all of these terms are positive, multiplying all of them does not change the direction of the inequality sign. And in the process of multiplication, there are terms cancelling out. So this F3 and this F3 will cancel out. Similarly, the F4 will cancel out with F4 right here, and so it goes on. And at the bottom, both Fn plus 1 and Fn will be cancelled out. So what remains on the left hand side is Fn plus 1 times Fn plus 2, and the direction remains unchanged. Now on the right hand side, 2 is multiplied n times, so we have 2 to the power of n, times F1 times F2. And F1 and F2 are both 1, so we have simply 2 to the power of n. Next, let's make use of this inequality. So if we replace Fn plus 1 here with Fn plus 2, then because Fn plus 2 is greater than Fn plus 1, we will have Fn plus 2 square is greater than Fn plus 1 times Fn plus 2, which is greater than 2 to the power of n. And now let's take square root. And since all of these terms are positive, taking square root does not change the direction of the inequality sign. So we have square root of 2 to the power of n, which can be written as square root 2 to the power of n. And now let's take a reciprocal of this inequality. When doing so, the direction of the inequality sign changes. So we have 1 over Fn plus 2 is less than 1 over square root of 2 to the power of n. And of course, this is still positive. And from here, we use the famous squeeze theorem. So if we consider the limit where n goes to infinity, this term remains 0, and this term will approach 0. So therefore, we can say that this limit is indeed 0. Alright, so with that, we have indeed logically proved that this reciprocal term indeed approaches zero. So now we can finally compute the infinite sum. So the sum of this infinite series is simply taking the limit to this partial sum, and using that this term approaches zero, we have 1. And that is our answer. So here we have solved this problem without solving the recurrence relation or using the general expression of the terms of the Fibonacci sequence. But in case you are curious, the actual closed form expression for the Fibonacci sequence is given like this. This expression right here gives the integer values for every natural number n. So you can plug in this expression in somewhere like here or here and try to calculate the sum of the series from there. But I am not gonna do that in this video, and I will just leave that to you. So that was all for today's video. Thanks for watching, and I will see you in another video.